I want to mention, so somebody asked, I got a couple of people that do this online, we're watching the recording, always ask me good questions. It's one person in particularly. And they asked me, so I thought this was a good time just to quickly do a quick review on the preferred, deprecated, invalid. How do global IPv6 networks keep track of which temp addresses are being used? Can they be used by other devices? Or are they only used once? So let's talk more about this again. I'm just going to go back to this one slide. So a device using stateless address auto configuration, okay, will create two addresses. Okay, it's going to create a public address and a temporary address. So let's look at the temporary address. Well, of course I go this, and let's go back one. Let's make sure we understand the difference here. So it's going to create a temporary address and a what we call a public, stable, permanent address, any of those. The temporary address, this is usually one address is what you'll see. 99% of the time, you'll just see one temporary address. And this is just like your regular IP address. Let's just call it IP, whether it's IPv4, IPv6, this is an IP address. This is what you can use anytime you're going out to the internet, doing anything, going out to a network, sending packets, this is what you use. Now, the difference with IPv6 is that there's no network address translation. So devices get to you using that address. Now, this is an address, one temporary address that will change periodically. We'll get to that next. Just because, as we remind ourselves, that interface ID, boy, that can uniquely identify you. If that never changes, that 64 bits is so unique in the world. It's 2 to the 64th is a lot. It's 18 quintillion. So, it's going to uniquely identify you. So we don't want to keep that same interface ID, no matter what, because say, hey, that's always you. Now, there is also that stable public address, permanent address, whatever you want to call it. And that's an address that we can use, or anybody from the outside can use, to access our computer that's in our network. Now, really, the only difference is this is an address that typically doesn't change, shouldn't change. Is there any reason why you can't use a temporary address to access it from the outside? No, except that it changes all the time. Okay, this is actually an address at least you should remember. You can write down or create, whatever. So you always know that address. It's also an address where you open up your firewall. Okay, usually your router, home router, firewall, here at Cabrillo, we have to open up, say, yes, I'm going to allow devices from the outside to come in to that address. Okay. So if that address is always changing, then you always have to change your router / firewall. So, but there's no reason why you can't access a client on the outside, can't access any IPv6 address on your device, whether it's a stable permanent public address or a temporary address, or one via DHCP, or one that you created statically. Doesn't matter. Okay. But we don't usually do this, do we? This is what we usually do. And this is where the emphasis is on stateless address auto configuration, is this temporary address. Now, just a note, we talk about this in my CIS 83 class, that, on an enterprise network, like here at Cabrillo, and we'll do this in CIS 83, on our router that connects our enterprise network to the outside world. There's a little side note, okay? We make sure that devices from the inside can get out. But the only way devices from the outside can get into our network is if that connection was initiated from the inside. So that's typically what we do anyway, that's what your home router does. Your home router says, by default, I only allow packets from the outside to come in if that connection was initiated from the inside. As a client, right? TCP, three-way handshake, we initiate that connection. Okay. So let's focus on this temporary address for a second. And so I can answer this person's question, which I did in email, but I thought it was such a good question. Okay, where's my new favorite? Here we go. Okay, so we create ourselves a temporary address. Okay, so we use the prefix of the router advertisement, but this interface ID, 64 bits, is going to have a lifetime. It's called the preferred lifetime. And this is really up to the operating system, how long it wants to keep it preferred. My Mac OS, and I believe Windows OS does this as well, is about 24 hours. So I can create anytime I have this preferred address, anytime I'm ready to go someplace, hey, let's use that preferred address, okay? I'm ready to do something else. Google, I need to probably put up pop, and I think this is what was confusing. So give me 1 second here. I'm going to add a couple more here. I'll just do this here. If I'm going to Netflix, great. If I'm going to Google, great. Doesn't matter where I'm going. If I'm going to, I got Netflix there, Google, I can go to LinkedIn. I go to my LinkedIn page here. Okay. So what I'm getting at is all of these, Netflix, Google, LinkedIn, they're all using this address. That's the point I wanted to make. Okay. It's not one address per connection. It's just like you're at home with IPv4 or at work. It's this one address being used for all of these connections. Okay. So for all those connections are using that one address. At some point, that lifetime is going to expire. Okay. And it's going to become deprecated. Now, and it's going to create a new preferred address. Now, what about these applications here? If I'm currently connected, let me go back. If I'm currently connected, when it went from preferred to deprecated, if I'm currently connected to these three, meaning it's the TCP three-way handshake, we're both maintaining state, neither one is timed out. They're all established. It's active connections, okay? Then I'm going to be using this address still for all those connections still, okay? But I will get a new IPv6 preferred address for any new connections. Now, let's say I'm not making any new connections right now. Okay, it's not being used. These are being used with the deprecated address. But as soon as I go to a new site, then now this address is being used, the new preferred address. Does this make sense? It's making sense? Okay. This is probably one of the most strange things, preferred, deprecated, but a lot of times you won't even notice the deprecated because you disconnected your computer, you logged off, and then the preferred address and all your connections expired. Then you boot up again or you connect again and you just have a preferred address and you start making connections. So a lot of times that's what happens. It's like 24 hours because they kind of figure you're going to go to bed. All right, so what happens to that deprecated address? Let's say all those go away. And let's pretend these go away too. You're no longer using any of those connections. Okay, then the deprecated address becomes invalid and is removed from the system. Okay. Make sense? Probably one of the most strangest things. Okay. It's kind of cool though, because it gives, a lot of privacy here. So devices can't be tracking us. Okay. I'll come back to that. I like that. My new favorite slide. All right. Today, um, I got privileged to be interviewed on a podcast a couple of weeks ago for somebody in Belgium about IPv6. And they asked me what was one of the toughest things about, what's one of the most challenging things for students to understand or anybody learning IPv6. And I said, well, the solicited node multicast kind of throws everybody off. So let's talk about that. It's not, you're halfway there, 3/4 of the way there, maybe more. Let's talk about solicited node multicast. And this will become clear today. Okay. So, in addition to every unicast address that we have, global unicast or link local, it will have associated with it a multicast address. Okay, so that temporary addresses we saw, the public IPv6 address we saw, the link local addresses that we talked about, they will all have automatically created a multicast address called a solicited node multicast address. Okay, so even here's a Cisco router. Okay, it has a global unicast address. I'm going to bring up my ink to go here, so I'm going to need that. Okay, right there. Okay. So in my Cisco router here, I have a global unicast address right here, and I have a link local address. Okay. Both of these are unicast addresses. So they are both have an associated multicast. So joined group. Group means multicast. Okay. Let's look at these real quick. This multicast, this is all multicast, right? FF is multicast. 02 means, well, the 2 here means link local scope, only good on this link, which 99% of the time, that's all we care about, okay, is communicating as a group on our own local area network. The 1 means all IPv6 devices. So this router will accept any IPv6 packets with a destination IPv6 address for all IPv6 devices, because it's an IPv6 device, just like your computer will. We'll see that in a moment. Here's another multicast group it belongs to, link local scope, 2. Remember we did the IPv6 unicast routing? Okay, this made it an all IPv6 routers. The other one was just devices. This is special. It's a router. Your computer doesn't belong to this. The router does. Okay, when we did the IPv6 unicast routing command, it said, oh, okay, I'll start being a router. When we created a global unicast address, and it created itself, looked like it used EUI64 here, first link local address, but let's do the global unicast address. When we created the global unicast address, it created its own solicited node multicast address for that specific global unicast address. When the device created its own link local address, it created a solicited node multicast address specifically for that link local address. Now, why in the world would it do that? Because it doesn't do that in IPv4. Okay? Well, here's the thing that we have to remember in IPv4. As far as the difference between IPv4 and IPv6. Ethernet and IPv6, and when it's IPv6 carried over Ethernet, so we have an Ethernet frame with any IPv6 packet. The one thing that we have is no broadcasts. No broadcasts. What does, okay? No broadcasts. That means no Ethernet broadcast. Remember in hex, it's all F, all 1 bit, 48 1 bits. Everybody has to accept this. In hex, there's not that in IPv6. Nope. Nope. It's got to be sent as a multicast. I'll just put MC. Oh, okay. No broadcasts. That means also in IPv6, no broadcast, no 255, 255, 255, no broadcast like that. Everything is a multicast. Why? Okay, well, I like what Jeff Houston said. I talked about a talk he gave last week, and I'll show that again here in a little bit. The talk I'm speaking of. And he kind of thinks, well, you know, somebody that was working on the people working on the IPv6 protocol. They're also doing some research on multicast, and so they threw multicast in there. So but it's actually a good thing. You know, you got to remember this was all at a time when you know bandwidth was at a minimum and CPU power was at a minimum as far as host computers. So we wanted to minimize what the host had to process. Let's remember that. Okay, let's continue. Okay, so every unicast address has a solicited node multicast address. Okay, let's look at this. This was from my house. Okay, as I had mentioned, we looked at this when we looked at multicast. This is the MAC address on my NIC card. It does accept, so it'll accept anything with a destination MAC address for its MAC address. It says, yep, you're this, I accept you. If you're a broadcast, there's that Ethernet broadcast, I accept you. But you know what? IPv6 doesn't use this. So in IPv6, okay, it has these it will accept these. Wow, look at all these multicast addresses. But before we get there, let's look at this here. Now we're going to look at this in more detail. Anytime we send something to all IPv6 devices, okay, this would be in the data here, the IPv6 destination address. Let's say we wanted to send something to all IPv6 devices. Isn't that like a broadcast, Rick? Yes. It is nowadays because everything speaks IPv6. So why not just make it a broadcast? Why does multicast even help? It does help. Okay, so if the destination IPv6 address is all IPv6 devices, okay, what the Ethernet multicast address would be is this. Okay, the NIC card's going to accept anything with this address as well. Okay, so in effect, it acts as a broadcast. Okay, this Ethernet MAC address in this situation acts as a broadcast. But we don't have to send everything as all IPv6 devices. You know, we're going to get there in a moment. You know, in ARP, we talked about this in IPv4. A device says, who out there has this IPv4 address? Send me your MAC address. It's a broadcast. We send everything as broadcasts in IPv4 if we don't know the MAC address. In IPv6, we don't have to do that. We don't have to send it to all IPv6 devices, and that's what we're going to get to here down here. So bear with me. Okay, we're going to get there. So let's get there. Instead of Rich just talking about it, let's get there. I said every unicast address has a solicited node multicast address associated with it. Here's a simple global unicast address. It will have a solicited node multicast address associated with it. Here's its link local address on that interface. It's going to have a solicited node multicast address associated with it. Now, maybe you can begin to see something. This isn't random, is it? There's some part of this that is not just, this is not just random. So solicited node multicast address. First of all, it begins with, this is ugly, 104 bits, okay? 16, 16, 16, 16, 16, 16, and then and then 8. Okay, I think that makes the 104. Yes, 8. So this part here is the 100. This here is the 104 bits. Okay. All right. So that's every solicited node multicast address, which is associated with a unicast address, is going to have that 104 bits. Okay, so we know that IPv6 addresses are 128 bits. We subtract 104. Okay, what do I have left over? 24 bits. So this here is 24 bits. Okay, 24 bits. Where did it get that 20? So when it created this, where does it look like it got those 24 bits from? Did it just make them up? I don't think so, does it? Look, hey, it says, let me grab these 24 bits. We're going to do this in a moment. And let's put it there. These happen to be a bunch of zeros before the 1. Remember, each one of these is 4 bits. Hexadecimal digits. Okay. There's my 24 bits. 16, 20, 24. So it says, let me grab these 24 bits and put it at the end. So that's how I get, this is the 104 bits here. All of that stuff. Oops, did I make them? Oh, yeah, no. Oops. There we go. Here's the 104 bits here. From here. And it added 24 bits. Okay, well, how's this used? Why are they making this so complicated, Rick? Let's take a look. Is it more complicated than it probably needs to be? I don't like to speak, criticize things that, of people that are much smarter than me and had a reason for doing things, especially at a time, 30 years ago when you're doing this. Who am I to judge? But yeah, it does seem to be complicated. So could they have made it simpler? Maybe. I don't know. Could we have changed it today? It's too late now. Okay. So, but let's bear with me. First of all, how are we doing on this? I'm going to show this more in a moment. Yes, Pamela.
Maybe it will become more obvious the more you describe it, but when you referred to like when they created this, it might be more complicated than necessary. If there's a way of circling back when this would be used and the purpose of why it was created, maybe I missed that and I apologize.
Yes, we haven't yet.
Oh, okay. Thank you.
So yeah, no, it's a great question. And I'm kicking myself because I know I'm dragging my feet on this a little bit too much. We're going to talk about how this is used. Okay, talk about how this is used. So let's get there. Then the advantages. Good question. Come on. Okay, so first of all, how it's mapped. it takes any unicast address. Okay, it takes the last 24 bits and adds it on to these 104 bits as we saw. Then this is why it does it, and part one of why it does it, and we'll get to part two in a moment. The Ethernet. This is for Ethernet and for the NIC card. Multicast is 3333. It's going to take the last 32 bits, the FF here, they're always FF, and the 24 bits here, and this is going to complete the MAC address. So what this means is this unicast address has been mapped to a solicited node multicast, which gets mapped to a MAC address. What this means is this device's NIC card is now going to listen for MAC addresses that have this as a destination MAC address. We're going to see this in a moment. Okay, so let me show you on my home device here what happened. These are my unicast addresses. You can ignore this, okay? This is my DHCP address, in case you're wondering where this came from. Okay, this here is my public address, if I remember correctly, and this is my temporary address. Okay. And this is my link local address. I'll just put LLA. Okay. This is just for when I'm communicating with devices on the network, like sending a router solicitation message. Uses that address. Says, yeah, I've got an address to look for a router. DHCP, yeah, I don't really use that. This is my temporary address. This is the one I use all the time until it gets changed. Okay. Now let's look at each one of those. Notice that it took the last 24 bits. I have it underlined. And we created a solicited node multicast address. The last 24 bits, it created a solicited node multicast address for each one of these. Okay, great. Then what? Then what created was an Ethernet MAC address, 3333, and then using the FF and the rest of this created a multicast address. So what this means is this: my NIC card, and here's part B, but we're going to get to part two, and then we'll see how it's used here in just a moment. My NIC card will listen destination MAC address, anything for its MAC address, anything that's a broadcast, and any of these. It says all of these is me. So when these unicast addresses got created, these multicast addresses got created, and my NIC card all of a sudden was told, accept destination multicast addresses, MAC addresses that are multicast belonging to these. These are for me. Okay. No broadcast an IPv6. Okay. So an IPv6, we're not going to worry about this. It's either this or any of these. Oh, and any of these as well. These are multicast as well, but these are for all IPv6 devices in this case. These are, oh look, that's a whole bunch of MAC addresses my NIC card is now going to accept as its own. Okay, let's see how this is used. Okay, I talked about why 3333 because Xerox PARC. Okay, let's see how this is used. In IPv4, okay, when we know the IPv4 address, but the device does not know the MAC address, well, first of all, it looks in its ARP cache, says, oh, I don't know your MAC address. I know your IPv4 address, not your MAC address, so let me send out an ARP request. So this device goes, yeah, that's my IPv4 address. Let me send you my MAC address. And that goes into the ARP cache. How about IPv6? Similar. What it sends out is something called a ICMP v6, similar, same group of protocols like router advertisement, router solicitation, called neighbor solicitation, neighbor advertisement. It says, I know your IPv6 address, but what's your MAC address? Let me check my neighbor cache. This is similar to an ARP cache or IPv6. It's a mapping of known IPv6 addresses to unknown MAC addresses. It's not in my neighbor cache. I know your IPv6 address. I don't know your MAC address. So what I'm going to send out is similar to an ARP request, but it's a neighbor solicitation message. Okay, we'll see that in a moment. And this device goes, yep, that's my IPv6 address. Let me send you my MAC address in a neighbor advertisement message. And it goes in the neighbor cache. Now, where does all this multicast come in? Let's take a look. In IPv4, okay, there's an ARP message with the IPv4 address, no IP header. It's sent as a broadcast. That means that device sends it and all the devices in the network have to look at it. What that means is all the network interface cards have to accept it. And this gets passed up to the ARP process in the operating system. And the operating system of every device on your local area network has to look at this target IPv4 address. And they're all going to say, no, it's not me, except for one, okay? Except for one device will go, that's me. Everybody else will go, it's not me. Okay? So operating systems are constantly in software having to look at these broadcasts. Hey, now this probably was more of an issue, or was more of an issue back in the 90s and early 2000s. Less of an issue today. Operating, our CPUs are much faster and everything, and can handle this. Not a big deal, but still, it's got to look at everything. Every operating system has to look at, is this my IP address? Everybody goes, no, except the one. Let's look at an IPv6. Same intention. It's looking for an IPv6 address. Okay? But this target IPv6 address is going to get mapped to a solicited node multicast address. This is IPv6 header. This solicited node multicast address is going to get mapped to an Ethernet NIC multicast address. We're going to see this in a moment. So when this neighbor, it's called a neighbor solicitation message, similar to an ARP request, gets sent out. It's not being sent out as a broadcast. We don't use that in IPv6. It's a multicast. It's one of those multicast addresses that only this host will probably have. I say probably, we'll talk about that. But let's say this host will only have. So what happens is when these devices NIC network interface cards receive it, the network interface card can go multicast. Is that that's not a multicast address I accept. Remember, we saw that these IPv6 unicast addresses get mapped, we'll see this again in a moment, get mapped to a multicast address, gets mapped to a Ethernet MAC address. If that's not one of the MAC addresses that belong to these devices, they're going to say, oh, I don't have that in my list of Ethernet MAC addresses that I accept. Let me just show you real quick. Let me open up my terminal here. Okay, I'm going to open up my terminal here. Let's take a live look. ifconfig EN7. This is my Ethernet connection. How do you spell ifconfig? There we go. So if you look at this, I have 1, 2, 3 unicast addresses. Everybody okay with that? I have my link local, I have my temporary, and I have my public permanent. Everybody okay with that? Okay. Now let me ask you, I have 3 unicast addresses. How many solicited node multicast addresses will I have on this interface? I have 3 unicast addresses. I'll have how many solicited node multicast addresses? Also,
3.
3, exactly. So the way I look at it, and I'll show you how to do this on Linux and Windows, I'm going to do the netstat command. This is how I got my other ones before. Netstat-g, and I'm just going to say, just show me EN7. Oh, grep. So what grep EN7. Okay, with this command here, netstat just G. G means group. Show me my multicast groups. And this, I'm filtering saying, show me only those entries that have EN7 in them. That's this interface. Okay. Now it's showing me a bunch of stuff here because it's showing me IPv4 as well. Okay. And it's showing me many different groups, but let's take a look at these. Okay. I know I'm going to have it for these 3. So let's look at solicited node multicast addresses. So here's my solicited node multicast addresses. Now, all I'm really interested in is the ones that begin in FFs, these here. So let's take a look. Our solicited node multicast addresses, right? Okay, they begin with F, so they are FF02, bunch of zeros, 1FF. So that's what I'm looking at. Solicited node multicast address. There's 1, 2, 3. I have 3. And are they associated with my, let's take a look. Let's do the ifconfig 7. Okay, this is an easier way to look at it. Okay, so let's find this one here. The last 24 bits, C826BE. CA, here we go. This is the solicited node multicast. Let me make this like this. This one here. I'm going to see the advantage of this in more, how it's used more in a moment. Okay, where's my BE? Right here. Right here to there, right? Maybe I can do different colors. Okay, there's that one. Okay, and oh yeah, look at this. With the FF involved, here's the Ethernet. My NIC card will accept anything for this MAC address. Why? Because it's based on this solicited node multicast address that was based on this global unicast address. Let's look at another one. Use a different color. Last 24 bits. 0C, where are you? B2, here we go. There you are. Yep, there's my Ethernet NIC card, but it all started here. The global unicast address was created, created a solicited node multicast address. Let's go 1, 2, and then this was created. Just like here. This address was created. This solicited node multicast address created this. And then my NIC card says, okay, I'll accept Ethernet frames for that. Let me do one more and then I'll get to that there. Let's see, let's use green here. Where's my link local? Here's my Lynn's local address created. Then this was created, then that was created. We're gonna see how these get used. Now my network interface card. So my network interface card is now saying, my NIC card, any Ethernet frames coming in for any of these, but let's look at these, for any of this stuff here. Anything coming in, I accept. Because this means it's most likely for me. Yeah, Pamela.
Thanks, Rick. So is the takeaway message, if we were gonna glean it, would be that, is it the single node multicast address enables the devices to, it's like a communication mechanism. It's like, okay, you can accept from these, otherwise I'm gonna ignore it. Is that what it's doing?
Yeah, it's basically telling the NIC, so it's a way, you know, sometimes I like to think of it as it's a way to do this. We have these 3 unicast addresses. 1, 2, 3. It's a way to tell our NIC card that, hey, these 3 these 3 IPv6 addresses, I may be getting Ethernet frame that is associated with these. Now, why not just use, why would a device need to send something to this Ethernet MAC address? Okay, so why does it need to send something to this? That's kind of the question, I think, right now, maybe. Why would that get used? Let's take a look. Okay, this is going to get used, as we're going to see here in a moment, and I'm going to see if I can catch it in case I need to use it again in this discussion. Okay, where it's going to get used is here. Okay. Okay. Did that already? All right. So let's look at this. Okay. So let's say this PC has the packet to send to this PC. It says, I know your IPv6 address, but I don't know your MAC address. Now there's other PCs on our local area network. It's going to send out what's equivalent to an ARP request. It's called a neighbor solicitation message. It's part of ICMPv6. And it says, this is the IPv6 address I'm looking for. Like in an ARP request, this is the IPv4 address I'm looking for. I need your MAC address. So it says, okay, hey, in IPv4, I'd send this out as a broadcast and everybody would have to see it. But I want to try and limit it so these devices don't need to look at it. This is the intent of doing this in IPv6, is to keep these devices to having even to check to see if it's them or not. That's the crux. So let's see how it does this. It says, I'm going to put this in an IPv6 header. I'm going to send this to a special multicast address based on the address I'm looking for. Notice this, 24 bits here, 24 bits here. And this is the special FF02:1:FF that gets prepended to it. Okay, I'm going to send it from my IPv6 address. Okay. Now, how do we keep these devices from having to look at it? Ethernet NIC. It's coming from my MAC address. Now, I can know this multicast address. This is whoever has this IPv6 address I'm looking for. Guess what? They're going to have a special MAC address associated with it. Why? Because they have mapped. So let's look up here. This is the device I'm looking for. It has mapped a solicited node multicast address to it, which has mapped a Ethernet MAC address to it. So this NIC card will accept anything to this destination MAC address. I know your IPv6 address. So I know I know that I can send it to this multicast address, but what I'm really using this for is to build a Ethernet frame, the destination MAC address. So I'm gonna send it to this Ethernet MAC address. So when this goes out, this NIC card here on this device says these are the MAC addresses. This is one of the MAC addresses I accept. My own MAC address, broadcasts, but I also accept this. Why? Because this address here was created, that created this, and then I was told to accept Ethernet frames for that. Hey, so I'll accept this. How about these NIC cards coming in to these devices? Okay. Chances are they are not going, and let's just say for right now, that they're going to say, no, my NIC card does not accept, is not been told to accept anything to this multicast. I'll accept it to my own IPv6 unicast addresses that get mapped. Like if I'm CCCC and I'm DDDD and I'm EEEE, you know, as far as this part here goes, hey, but that doesn't map to this multicast Ethernet address, so I don't even have the NIC card in hardware can go, nope, this quote unquote ARP request, neighbor solicitation message, cannot be for me. Because I don't even have an IPv6 address that maps to what you're looking for. This is probably the hardest thing to comprehend in IPv6. And I think of ways that they could have made this much better. But I'm not going to criticize them. You know, they're smarter than me. Okay, but that's the idea.
I'm sorry.
No, go ahead.
I was just gonna say thank you for saying that because I'm trying my best to absorb everything and connect the dots, and it's really challenging. So I'm glad you said that.
And when I got interviewed on that podcast, this is why. I said, this is the hardest thing for people to comprehend. Because it's like, well, you know, it just adds an incredible layers of complexity to a simple process of art. And even, and I'm going to show you some examples here. We'll take a 5-minute break here, 8-minute break. But even, let me go to my YouTube channel. So if you go to my YouTube channel, okay, you'll see this here, Nanog IPv6 view full playlist. So this is Jeff Houston, spoke at Nanog.
V6 kind of gets lost.
Okay, talks about, he's been around forever and been a part of understanding, he understands we need to go to IPv6, but he also understands that, you know, we've done a lot of things to slow that need down in many places. That's what this talks about today. This is a great video. It's an hour, but he does a great job of talking about, you know, the history and why with things like NAT, but also cloud, Anycast addresses, some of the things I've introduced at least, not that you understand it all in IPv4 or in CIS 81, but things that have kind of kept, at least for the enterprises, IPv6 at bay. But he also talks about that, he says, you know, we made it more complicated in some ways than it needed to be. You know, we're eventually going to get there, but, you know, yes, it's complicated. And he even admits that it was more complicated than it needed to be. And this is one of those things. Wow, really. And the reason why, and we'll take a break here. The reason why was so we don't have to use broadcasts. That was the whole idea, was no broadcasts here. I'll just BC, no broadcasts. So these devices normally broadcast, everybody has to accept it. So they're trying to keep that from happening. No broadcasts. Let's send these messages only to the NIC cards that really need to look at them. And you know, back in the 90s and early 2000s, that was probably more of an issue than it is today, to be fair. And I think if there's one thing that they would maybe relook at, it, you know, and I'm just speculating, it's this. Was this really required? Okay. I don't see really the need for it so much anymore. Okay. So I would say no. But this is one of those things that people pull their hair out going, oh my God, what is this? So when we come back from the break, what I am going to do, show you, is we'll look at the actual message, see the mapping of it in Wireshark. Okay, let's do that. Let's take an 8-minute break. Good questions.
Recording stopped. Recording in progress.
All right, let's get back to this. Some question there. At the end, John, ask me again, make sure that, I'm not sure what exact, I think I know what you mean, but I just want to make sure. Let me show this here, because I'm going to talk about something called, similar to the ARP table. And maybe that's what this is, it's associated with. Here's a neighbor solicitation message from that device. So this is like an ARP request. It says, it's an ICMP v6 message, type 135, code 0, which means neighbor solicitation. This is the address it's looking for. It needs the MAC address associated with this address. Okay. So what it does is it builds an IPv6 packet and says, okay, since I know the address I'm looking for, the unicast address, I can grab this last 24 bits and put it in a destination destination IP address that's a solicited node multicast. Because I know if you have this, whoever has this IPv6 unicast address will also have an associated multicast address, solicited node multicast address associated with it. So let me grab these 24 bits, put it on the end of this, 104 bits. Now, if you have this, whoever has this solicited node multicast address is also going to have this, have on their NIC card, say, I'm going to be listening for anything that's 3333 FF in the last 24 bits here. Well, the FF had 32, but these last 24 bits here. Okay, so that's how it says, hey, if you have this unicast address, then you have this multicast address, which means you're listening to this MAC address. Does that make sense? So that means not everybody's going to accept this. That's the weirdness behind it. So instead of saying it's a broadcast, this will help narrow who may look at this. Now, is it possible more than one device may have this? Yes, we'll talk about that in a moment. Okay. So looking at solicited node multicast addresses. So on Windows, you know, if you do IP config, it'll show you your link local address. Even if you don't have a global unicast address, you have a link local address. If you do net sh interface IPv6 show joining which groups it joined, okay, it's going to show, if you do, at least it will show your link local address. Here's the solicited node link local address. If you have a global unicast address, it will show that too. These are the solicited node multicast addresses. You'll notice some FF02:1 FF. And then the last 24 bits associated with the unicast address. In Linux and Mac OS, it's just netstat-g. So I showed that earlier, and I can show that again on my Mac. Same thing works for a Mac. Okay, so IF config, just look at that EN7 interface, Ethernet network interface 7, my link local, one of my global unicasts, my other global unicast. One's public, permanent, one's temporary. Okay, and if I do look at netstat-g for just that interface, then again, I see my associated solicited node multicast and then the MAC address. Okay. So again, the advantage of this, you've seen this before, is that the NIC, not all NIC cards have to accept it. Not everybody has to look at the ARP request like an IPv4. Nope, that's not going to be somebody looking for my IP address because I don't have a solicited node multicast associated with that, which means the NIC card can go, nope, I can tell you right now, this isn't going to be for me. Okay, so here's another example, we're pinging this device here. I know your IPv6 address, what's your MAC address? I look in the neighbor cache, it's not there. Send out a neighbor solicitation message. So since I know your IPv6 address, I can create which is the target address I'm looking for. It's the address I'm looking for. I know you have a destination, you'll be accepting packets for this destination, multicast address, Solinode multicast, last 24 bits. And you'll also, did I not put it there? I did not put it there. I know the NIC card will also be accepting Ethernet frames with this destination MAC address. Others will not. And in this case, device, yeah, this is mine, I'll send you, and there we go. All right. Gonna show you another example here. Yeah, yes, this is, I wanted to make sure I show this. Is it possible that two devices, PCA and PCB, will accept frames for the same solicited node multicast address? Yes. So here we are. And this is one of the things I don't know why they did it this way. Okay, here's our interface ID. So our interface ID, here's the first 16 bits. And then here's the rest of the 64 bits. So remember, we got 64 bits for the interface ID. This is the first 16 bits. Then we have a bunch of zeros. Here's the last 16 bits. And then we have 32 bits here in the middle. That's all zeros. What if both of these devices have the last 24 bits in common? Now, the interface, they're on the same network. Their unicast addresses are unique. This one has the first 16 bits all A's. This one's first 16 bits all B's. So their interface IDs, which is this part here, is unique. That is unique. But the last 24 bits are not. So they will both have solicited node multicast addresses mapped to different unicast addresses, which means, yes, they will have Ethernet MAC addresses mapped to the same solicited node multicast addresses, meaning they'll both accept Ethernet frames going to this destination MAC address. They'll both accept it. So this is the rare case where this can happen, but it's not a problem. Let me explain why. Okay, so let's say a device is looking for this address here, down here. This is the address I'm looking for. It got mapped to this solicited node multicast address, which got mapped to this MAC address. Now, both of these actually have the same last 24 bits in common. But the part of their interface ID, this makes it unique, the first 16 bits. So they're both going to be listening for, if you see what they got mapped here, this got mapped to this solicited node multicast, that got mapped to this MAC address. Same thing here, got mapped. So they're both listening to the same Ethernet MAC address that's a multicast. Only because the last 24 bits are in common. Only the last 24 bits are in common. But they're both accepting the same MAC address associated with different unicast addresses. Not a problem. So when the Ethernet gets it, says the NIC card will go, yes, it's for me. Or possibly at least. They'll both hand it off to their IP process. Their IPv6 process says, yes, I accept multicast addresses for this, I accept those. this destination IPv6 address, yes, I accept those. In this case, it'd go all the way up to what's similar to an ARP process in IPv4. It'll be handed off to the neighbor solicitation product, ICMPv6. And that's where they'll look at the actual address itself. When I say the actual address, they're looking at what's in here. Okay? They're looking at what's in here. And they say, you're looking for AAA 200, you're looking for AAA 200. This one goes, yes, this is for me. That's my address. Yep, that is me, for me. This one goes, this address? Nope. Got close, but no. Got close, but that's not one of my addresses. So it does not return a neighbor advertisement message. It does not return a message, yes, this is for me. This one does. Oh, let me send you my MAC address. So this one sends the reply back. This one does not. Okay. So that's the rare occasion. Okay. And it figured that, you know, at least 24 bits, that's got to be at least, you know, what are the, you know, most devices, especially using Slack. You know, if you're using Slack, what are the chances that, let's take a look at Rick's address again. Just what I have right here. Let me get this out a little, let me get it a little smaller version. What's the chances that anybody else is going to have the same IPv6, at least, you know, the same last 24 bits as Rick? Who's going to have just these last 24 bits? What's 2 to the 24th? Is that over 16 million? Okay, so if we're doing this randomly with Slack, with random addresses, with Slack, or even EUI64, right? Chances are, you know, in EUI64, the last 24 bits are going to be unique, which is, you know, why they chose 24 bits. Okay, the first 24 bits is the vendor portion. This will be unique, so let's just check the last 24 bits. That's why they chose 24 bits here. You know what's funny? I just realized that. You know, that's why, well, I think I did before, but that's why they chose to use 24 bits in the mapping of the solicited node. Does that make sense? I mean, it's just kind of a, you know, the chances are this is going to be unique, especially with EUI64 random, man, 1 in 16 million. Yeah. So let's just check the last 24 bits. Yeah. It's, you know, it's a nice way of doing things. Okay. If you have these, you know, but it's also maybe as far as adoption of IPv6 has made it a little bit more, it shouldn't stop you. If you understand this, that's fine. If you saw it just this once, this is one of those things I put in the back of my mind. If I need to explain it to somebody, then I'll pull it out and look at it again and figure it out again. Okay. I'll look at Rick's video again, maybe. But other than that, just know, yeah, it doesn't use broadcast, but it uses a multicast address that gets associated with an Ethernet MAC address to limit what, you know, that not everybody, NIC card has to process it. For efficiency reasons that probably aren't needed as much today. Okay. But I like it only because it's like, well, you have to make sense. It's a, you know, but is it kind of really getting too picky today? Maybe. I think it's definitely made things more difficult in how we think about it. Oh, those quizzes. So somebody asked about the quizzes. There's no quizzes. Those are just check your understanding. if you want to look at those. Okay, but there's nothing associated with this. John, did I answer your comment question? I haven't talked about the ARP table, which we are gonna talk about on Tuesday next week. Called the neighbor discovery table.
No, it was just, when you were talking about the temporary addresses, them going away, it finally, the idea popped in my head that the equivalent of the ARP table for IPv6, those addresses age out. And when the temporary address goes away, the router entry is gonna go away, and so it really doesn't exist on the network.
Yeah, so we are going to talk about this on Tuesday. This is my ARP table in IPv4. I should just, there we go. So this is for, actually, if I just do the grep EN7, let's just. So this is my ARP table for IPv4. These are the, interesting. What network am I on? But showing me my MAC address mappings. Oh, let's look at it real quick here. Oh, okay. Oh, I'm on a different network. Okay. So, this is my IPv4 address. Okay. So, it was throwing me off because I'm used to being in one of the other classrooms. So this is my default gateway. This is its MAC address. Okay. I don't know if anybody else is on this network, but I would, I only know devices on my IPv4 address and that network. If I wanted to do the equivalent for IPv6, we're going to look at this on Tuesday. It's called NDP, Neighbor Discovery Protocol, instead of ARP-A. And let's just look at it for this interface. And you're going to see something a little different. Yes, this is another thing they made a little bit more complicated.
Hey, Rick,
did they really need to do this? It's another one of those things. At the time, it sounded like a great idea.
Rick, I have a question.
Yeah, one second, let me just, this thought real quick. Here's the IPv6 addresses to MAC addresses, but we're gonna see different states, reachable, stale, etc. at a time. Yeah, Roger.
So I've been doing the quizzes. I was thinking that was part of what we're supposed to do. By now you say the quizzes are not. What are we?
You don't have to do them. No, they're just for your own, check your
But
understanding.
what are we supposed to be doing to get a grade?
The grade, I told you at the beginning of this, that all you need to do is get out of this what you want to get out of this.
Okay.
You'll get a good grade, okay?
So we
Yeah.
just have to sit and listen, and if we want to
You don't
get more
have-
out of it, we do the quizzes and stuff. And
Okay, so there's the quizzes are just something that you can do on your own. So what I said at the beginning, I sent out the email about this as well. that
you
this
said it was like a
s-
seminar.
Yeah, that, because this is the last 8 weeks of people, and people have other classes and stuff, that I want to make sure that people got the information, got an understanding of it. Okay, and not worry about, I'm listening to the lectures, I'm attending the lectures, I'm emailing Rick questions, but, I don't have time for labs and do a bunch of homework. That's what I wanted. I didn't want people to drop because of that. I just want people to
okay.
make sure they got this information.
Well, I do get a lot out of the quizzes.
Okay, good. Yeah, that's why I made them optional.
Okay.
So they're not required, but they are optional. And I am gonna put a little exam at the end. And the quizzes should show you the answers, correct? Yeah, I'm gonna do the same thing for an exam at the very end. that's kind of a review of everything that you can take if you want, just shows you the answers.
We love seminars. Thank you,
Yeah.
Rick. It
Yeah.
really helps. Yeah, it takes the pressure off, but we could still learn, you know?
And that was kind of the whole idea. It's kind of like going through a training class where you don't feel the pressure of, you know, I need to keep my GPA up or anything like that. So, I hope this works for people. That's why I mentioned it right at the beginning. You know, if this is okay with you, fine. If it's not, then, you know, I'm assuming that everybody understood that and is okay with that. Okay, because I wanted to put more energy into this, talking about it, sitting together, understanding it. And, you know, so, all right. All right, looks like we're at that time. So at the next week, first of all, happy Thanksgiving, everybody. And then on Tuesday, we're gonna continue talking about this a little bit more. Talk about the ARP table and how that's a little different. Another one of these extra complexities that they added. Is it a good thing? You know, we can talk about that. You know, I'm not one to judge the reason why they did things. They just tried to, you know, use IPv6. They said, you know, let's just kind of keep the same thing, a lot of this the same, but if we can enhance it, that's a good thing. Now, anytime you enhance anything, you're always adding to it, right? And that's what happens. So they added some stuff, timers, different states. It's just not whether it's in the table or out of the table. Which it could be a good thing. So again, it was at a time when we were more worried about, you know, the, the, the processing of CPUs and whether or not, you know, you're trying to minimize that today, you know, so much of our CPU, especially on our client devices are not at its full peak, and can process things as they come in and out of the NIC cards pretty quickly. But, you know, it was in a way a smarter way of doing things. Was it necessary? I don't know. You know, I think that's up for debate. Okay, I'll let you go. And I will, happy Thanksgiving, everybody.
Thank you.
Be safe out there.
Thanks. Happy Thanksgiving.
Thank you.